June 18, 225. Just past 317 UTC, NASA's live feed tracking 3-2 Atlas, the third confirmed interstellar visitor to our solar system, suddenly cuts out, but not before a single baffling frame appears, hinting at something that doesn't look natural. Astronomers rush to verify. Was this a technical glitch or a genuine artifact? NASA's official logs confirm the blackout with mirrored data matching across independent archives. And here's what sets the stakes. 3EA Atlas was already a cosmic outlier, but now the evidence chain suggests the anomaly wasn't a random failure. Some researchers wonder, could this last image really show something engineered? So, how do you even begin to prove it? Before we break down the moment-by-moment timeline, comment below. Is it possible we just missed our first glimpse of an artificial interstellar object? The real story starts here. The last recorded frame from NASA's live feed arrives stamped 031712 UTC, just fractions of a second before the blackout. At first glance, it's a standard commentary image. Dim nucleus, blurred coma, faint tail, all set against the cold black of deep space. But then something catches the light. A razor-straight glint slicing across the lower left quadrant. Not a curve, not an arc, an edge. Geometric, sharp, and at odds with the soft natural contours everywhere else in the field. Edge detection algorithms run by independent astronomers flag the anomaly within hours. The software picks out a line segment almost perfectly straight, measuring about 37 pixels end to end, reflecting sunlight at an angle that doesn't match any known debris, cosmic ray artifact, or camera glitch. The reflection is too consistent, too crisp. Under natural conditions, comet dust scatters light in irregular, diffuse streaks. Here the light bounces as if off a polished surface. Some suggest it resembles the glint you'd expect from machined metal, not fractured ice or rock. The timestamp matches across all mirrored archives. 031712 UTC with cryptographic hashes confirming the frame's integrity from NASA's official relay to at least 3 independent data repositories. Citizen archivists in Australia and Germany running continuous packet captures upload their copies within minutes. Every copy matches. No sign of tampering. The anomaly appears in every version regardless of compression or color balance. No one claims to know what the edge truly is. Some propose a chance alignment, a background star momentarily intersecting with a dust fragment, creating the illusion of an artificial line. Others argue the angle of reflection is too precise, the geometry too deliberate. Spectral analysis of the glint shows a spike in the visible band with a secondary peak in the near-infrared, consistent with polished alloys, but also with certain silicate minerals under the right conditions. If this edge is artificial, it would be the first such signature ever recorded from an interstellar visitor. But if it's natural, it's a coincidence that defies easy explanation. For now, the frame sits in digital limbo, neither confirmed nor debunked. The debate rages in comment sections and physics forums. Natural artifact or a glimpse of something engineered? The blackout that follows only deepens the mystery. Was it a simple technical hiccup or a system reacting to data outside expected parameters? The official line is network instability, but the timing down to the second keeps the question alive. If a comet can throw a perfect geometric shadow across a NASA feed, what else might slip through before the next blackout? Raw data from the NASA feed wasn't just captured in a single place. Within minutes of the blackout, independent archivists in Australia, Germany, and the US uploaded their packet captures. Each file labeled with the same 031712 UTC timestamp carried a unique cryptographic hash. Long strings of numbers and letters that serve as digital fingerprints. When compared byte for byte, every copy matched, not a single pixel out of place, not a single frame missing. The hash for the Australian archive ending in 4F8D matched the German mirror and the original NASA relay. No evidence of tampering, no sign of post-processing. Citizen archivists have become an unofficial backbone for space data integrity. They run scripts that watch public feeds, grabbing ROTS files the moment they're broadcast. Each file is immediately mirrored to decentralized platforms, academic data vaults, blockchain-based timestamping services, and even encrypted torrents seeded by volunteers. Source URLs for these archives appeared on astronomy forums within hours along with 256 checksums anyone can verify. The process is methodical. Download the file, run the hash, compare results. If even a single bit changed, the hash would break. But every copy, everywhere still lines up. These archivists log their actions in plain text, usernames, UTC times, server locations, all preserved in public ledgers. The first mirrored copy appeared on a German university server at 032107 UTC, followed by an Australian science mirror less than a minute later. Each upload included a hash, a file size, and a direct link to the original NASA relay. The American node, run by a retired network engineer in Ohio, posted his checksum and a signed statement to a public JIT repository. Anyone can audit the trail frame by frame from NASA's downlink to the far corners of the internet. Timestamp corroboration comes from multiple sources. The packet capture logs, the mirrored archive server clocks, and even third-party time authorities like NIST, all align to the second. The blackout frame 031712 UTC shows up in every archive, no matter the source or compression. No later frames exist. The feed resumes only after the anomaly has passed, leaving a gap that's identical across all versions. This isn't just redundancy. It's forensic-level transparency. For those chasing explanations, the integrity of the evidence is a rare constant. The chain of custody is airtight. From NASA's own relay to the mirrored archives with hashes and timestamps to prove it. The edge in the last frame, the glint that set off a storm of debate, is preserved in every copy, immune to claims of digital manipulation. If there's a mundane explanation, it won't be found in missing data or altered files. The question isn't whether the anomaly was captured. It's what exactly that edge means. Before diving into technical analysis, the record stands, the data is real, the archive is clean, and the mystery remains untouched. But what happens when technical experts start breaking down that frame pixel by pixel? Comment if you've ever tried verifying a cryptographic hash or tracked down a mirrored archive. The next layer of scrutiny is about to begin. NASA's live feeds rely on a maze of ground stations, relay satellites, and automated handoffs. The Tracking and Data Relay Satellite System, TDRS, sits at the heart of this network, bouncing signals between orbit and Earth. Every image, every pixel travels through a chain of hardware and software checkpoints before reaching public screens. A typical feed from a space telescope or planetary probe passes through at least 2 satellite relays, then down to the Deep Space Network. From there, it's routed through them Hydra data centers, often switching between nodes in California, Spain, and Australia, depending on the object's position and Earth's rotation. Dropouts aren't rare. Most are routine, built into the system. When a relay satellite moves out of line of sight, there's a handover. Sometimes seamless, sometimes not. A classic sign is a 2-second gray screen, the digital equivalent of static. Engineers call these handover blanks. They show up as a sudden loss of image, a brief pause, then the feed resumes as the new link stabilizes. The timing can look suspicious, but it's usually just orbital mechanics. If a telescope tracks an object as it sets behind the Earth or dips below a satellite's coverage arc, the data stream cuts. No drama, just geometry. The Deep Space Network logs every dropout. Each interruption comes with a fingerprint, start time, duration, and often a reason code, handover, packet loss, relay outage. These fingerprints match across mirrored archives. The pattern is so consistent that ground segment engineers can spot a routine handover cut from the dropout length alone. A 2-second gray screen, then back to normal. That's standard. No hidden switch, no manual override. The system is designed to recover automatically without human intervention. Most of the time, the only clue is a timestamped gap in the log files. For anyone chasing anomalies, these technical fingerprints matter. Comment if you've ever seen a live feed drop mid-broadcast or tried to trace a signal handover. The next question: when does a dropout look like more than just a routine glitch? Digital forensics teams wasted no time pulling apart the last frame. They zoomed in on the sharp glint, tracing it pixel by pixel. The first thing that stood out: the edge ran perfectly parallel to the borders of several 8x8 pixel blocks. That's not a cosmic coincidence. It's a fingerprint left by the video codec itself. NASA's feeds, like most space video, use heavy compression to save bandwidth. The algorithm slices each frame into a grid of blocks, then stores only what's changed. When a sudden flash or a straight line lands just right, the codec can exaggerate it, snapping faint streaks into rigid, blocky outlines. But compression isn't the only culprit. Space cameras are bombarded by cosmic rays, high-energy particles that can slam into a sensor and leave behind a white-hot streak. These hits are usually random, but under the right conditions they can carve out lines that look eerily geometric. Forensic analysts flagged a transient white streak in the lower left, lasting just a single frame. That's textbook cosmic ray behavior. Brief, bright, and gone in a blink. Macro blocks and cosmic rays both leave their mark, but neither explains everything. The edge's alignment with the pixel grid raises questions about whether the glint was sharpened by the codec or born in the sensor itself. Some propose a double hit, compression amplifying a real fleeting artifact. Others point out that geometric shapes can emerge by chance when cosmic rays, compression, and background noise collide. If you've ever seen a glitched video or a corrupted JPEG, you know how digital ghosts can mimic order. But none of this rules out the possibility of something more. Comment if you think a perfect edge can really be just a glitch. Next comes the real test. Does the object itself show signs of the unnatural, or is the anomaly all in the pixels? 3E Atlas stands as only the third confirmed interstellar object ever detected passing through our solar system. Its name comes from the system that first caught it, the Asteroid Terrestrial Impact Last Alert System, or ATLAS. This network of telescopes stationed in Hawaii, Chile, and South Africa scans the sky every night for anything moving against the background stars. When ATLAS flagged 3I Atlas on July 1, 2025, astronomers quickly realized this was no ordinary comet. Its trajectory was hyperbolic, meaning it wasn't bound to the sun. It was just passing through on a one-way trip from deep space. The first images showed a fuzzy coma and a developing tail. Classic signs of cometary activity, but the details set it apart. 3 Atlas is unusually rich in carbon dioxide. Spectroscopic studies from the James Webb Space Telescope and ground-based observatories revealed a carbon dioxide to water ratio of about 8:1, far higher than most comets from our own solar system. That means carbon dioxide is driving most of its outgassing, not water ice. The coma itself stretches hundreds of thousands of kilometers, and the dust cloud is dense enough to hide the nucleus from direct view, even for Hubble. Estimates put the solid core somewhere between 320 m and 5.6 kilometers across, but most likely under a kilometer, comparable to 2E Boros, the last interstellar visitor. The Atlas survey's cadence, scanning each patch of sky 4 times a night, helped catch 3 Atlas early while it was still far from the sun. That gave astronomers a rare chance to watch an interstellar comet wake up as it heated. The initial uncertainty, asteroid or comet, vanished within a day as images from Chile, Hawaii, and Arizona all showed a faint expanding coma. Within 24 hours, the Minor Planet Center had designated it 3I Atlas, confirming its status as a visitor from beyond. The global response was immediate. Telescopes worldwide scrambled to secure early spectra and photometry, knowing this was a fleeting window. Atlas's role in this discovery highlights just how much the field has changed since Oumuamua slipped by with barely a week of notice. With every new interstellar object, astronomers refine their search strategies, hoping to catch these cosmic messengers earlier and study them in greater detail. If you've ever followed dead-alive comet discovery or tried to catch a new object in your backyard scope, share your story below, because the next anomaly in 3I Atlas's behavior is about to bring even more surprises. Every claim about something artificial in space faces a steep climb before it's accepted as fact. The process begins with raw observation. A flash, a line, a glint flagged by automated systems or sharp-eyed astronomers. But that's just the first rung. To move higher, the anomaly must survive a gauntlet of scrutiny. Independent teams must see it in their own data using different telescopes and instruments. If one observatory reports a geometric edge, others need to confirm it, ideally across different wavelengths from visible light to infrared. Only then does it reach the level where peer review even starts. At each checkpoint, scientists ask, is this a real signal or an artifact of the camera, the software, or the environment? For 3 Atlas, the evidence so far sits low on this ladder. A single frame, a possible edge, a handful of spectral hints. No multi-instrument confirmation. No independent team has pinned down the same artificial signature. Until those higher rungs are reached with matching data from Hubble, Webb, and ground-based scopes, most researchers hold back. They want to see the same anomaly at the same coordinates with the same properties in more than one data stream. That's how something goes from oddity to candidate and from candidate to discovery. If you've ever chased a wild claim only to find it vanish under closer inspection, share your story below. The real test for 3I Atlas is still ahead as the search for repeatable multi-source evidence continues. 3 paths split the debate wide open. The first leans on physics. Shards of rock and ice breaking off the nucleus. Sunlight heating the surface. Jets of carbon dioxide erupting from beneath the crust. When those jets fire sideways, they can torque the nucleus, twisting its spin and even sending fragments drifting in unexpected directions. Measured torque values from carbon dioxide jets on 3I Atlas are strong enough to change its rotation period by hours over a few weeks. If the edge in that last frame is real, one interpretation says it's just a fresh fracture. Sunlight glinting off a new face of ice that split away under thermal stress. The second path points to chance, a collision of cosmic rays, digital compression, and a dust particle lined up at just the right moment. An accidental illusion, not an engineered artifact. Algorithms flag false positives all the time, especially when a single pixel line can be amplified by the codec's blocky math. Many in the community still favor this, arguing that the simplest answer fits best. But a third idea keeps resurfacing. Some propose the edge hints at something more. A probe, a manufactured object, or a shell designed to survive the cold vacuum of interstellar space. If the glint comes from machined alloy, not fractured ice, then we're looking at a message or a machine, not a comet. The odds are long, but the possibility lingers. If this is artificial, every assumption about what travels between the stars needs a rewrite. Which path feels most convincing? Comment below and consider. Whatever the answer, the next observation could tip the scales for good. A single frame of data can ripple far beyond the walls of a lab. When a NASA feed cuts at the exact instant anomaly appears, it does more than spark debate among astronomers. It sends a jolt through public imagination and scientific policy alike. Suddenly, the question isn't just about one comet. It's about who controls the flow of discovery, who decides what's seen and what's hidden, and how quickly the world can mobilize to chase the unknown. Funding priorities shift. Lawmakers asked for new protocols on data transparency. Research teams push for more open archives and real-time mirrors, arguing that the next anomaly could rewrite the textbooks or expose a gap in our vigilance. For everyone watching at home, the event becomes a test of media literacy. Is this a glitch, a cover-up, or a hint of something bigger? The next time a feed drops, more eyes will be watching, more questions will be asked, and the line between skepticism and wonder will blur just a bit further. If even one frame can change how we search the skies, what happens when the next visitor breaks all the rules? At 3:17 UTC, the NASA live feed documenting 3I Atlas was interrupted. The final captured frame showed a straight-edge glint that some found strikingly artificial. The footage's integrity was verified by matching raw file hashes and mirrored timestamps, confirming no tampering occurred during archival. Technical review traced the feed drop to routine relay handoffs and identified camera sensor artifacts, both common in deep space imaging. Yet, the timing of the blackout coinciding with the unusual visual anomaly remains officially unexplained. 3 Atlas stands as the third confirmed interstellar object discovered by the Atlas Survey and catalogued as a carbon dioxide-rich comet. Peer-reviewed analysis requires multi-instrument data before any claims of artificiality can be made. As of today, no conclusive evidence supports either a natural or engineered origin. The unanswered question why the feed cut at that exact moment still fuels debate. What is clear, every new visitor from beyond our solar system pushes our technology, our curiosity, and our standards of proof forward.